Am I audible?
Yes, ma'am.
Okay. We'll wait for 2 more minutes for others to join, then we'll start.
Okay, ma'am.
So we'll start now. Good evening. Welcome to the live session of course Waste to Energy Conversion, instructed by Professor P. Mondal from Department of Chemical Engineering, IIT Roorkee. I am one of the TA for this course. I am a PhD scholar at Civil Engineering Department at IIT Kanpur. So basically what I do is I give a brief recap of what was taught in the previous week. Then we try to solve the assignment questions, previous year assignment questions, followed by one or two more questions. So first I want to ask you if you have any doubt or something, any problem in understanding the content or solving the assignment.
No, madam.
Okay, you are not audible. Okay. No, okay, then we'll proceed. So in week 3, there was one lecture on gasification, one of the gasification lecture, followed by 2 lectures on pyrolysis. So we'll start. We have done till the types of gasifiers, that was fixed bed, fluidized bed, and entrained bed. These are the gasifiers which are used for coal gasification. For biomass gasification, these gasifiers adapted from coal gasifiers. So first is fixed bed. These three differ in their combustion temperature, how much pressure is required in the reactor, what is the particle feed size, and what is the retention time. So among these, so maximum temperature is in fixed bed, but here we can feed the particle size between 2 to 50 mm. But in fluidized bed reactor, the combustion temperature is relatively less and particle size is also less, because what happens in fluidized bed that the biomass as well as the air which we provide both are in continuous motion. That's why the particle size are kept smaller here. Then in entrained bed, it is more efficient as compared to the other two, and the combustion temperature here is about 1500 degrees centigrade. So we can see here that the gas which comes out from the reactor has different temperature also, depending on the reactor which we are using. So next is these are the gasifiers which we use for biomass burning. First is fixed bed. Fixed bed are of two types. First is updraft, in which waste and air are provided in different direction. And then is downdraft. It is also based upon on the point where we apply waste biomass and the air for burning. Next is fluidized bed. In fluidized bed, we have three types of reactor: bubbling fluidized bed, circulating fluidized bed, and double fluidized bed. And we have entrained bed. One more addition is for biomass burning is the gas plasma gasifier, which is more efficient than these three. So first we will see what is fixed bed gasifier. Here you can see in the left, it is a updraft fixed bed gasifier in which the biomass is added from the top and air or oxygen, whatever we are providing, we are adding from the bottom. And we are getting the syngas from the top. So there is a counter current flow between biomass and air. And because of this, the contact time between biomass and air is not that much. And so the syngas which we get is not that efficient than downdraft flow. But the advantage of this reactor is it is simple and inexpensive. It gives satisfactory result under pressure. There is low dust level in the gas, etc. So next is downdraft. What happens here is that we provide the biomass from the top of the reactor, and thus when we provide steam and air from the two sides of the reactor. So when mixed the air or steam and the biomass all flows in one direction. So it is concurrent flow, optimum time is provided, and the gas we get from bottom and the whatever left we take out as ash. So in this reactor, it is suitable for small scale engine applications. So it is better than the upward draft reactor, but it is inferior than fluidized gas and other reactors. So these are the next is fluidized bed reactor, gasifier, sorry. These are the three types. First is bubbling fluidized bed, next is circulating fluidized bed, and then dual fluidized bed. So in bubbling, difference between bubbling and circulating fluidized bed is only of the air velocity which we provide. In circulating fluidized bed, we provide more velocity, more air velocity as compared to bubbling fluidized bed. And because of the high velocity, there is a chances that the biomass may get carried away with the syngas. So after separation from the syngas, it is the biomass particles are recirculated back in the reactor. And in dual fluidized bed, we have two different reactors. In one, we provide the air, and in other, we provide the steam. So first, in the first reactor, air is provided, and the flue gas is taken to the second reactor, where again steam is provided and biomass is further broken down into smaller components, and syngas is taken out, and the rest biomass, which are not degraded, are sent back to the first reactor. So fluidized bed reactor are obviously better efficient, are better than the fixed bed. And also they have high volume capacity than the fixed bed reactors. Here the gasifier temperature is between 500 to 900 degrees centigrades. Next is entrained gasifier. In entrained gasifier, we provide all the three: steam, biomass, and oxygen from the top. So ample time is provided for the particles, biomass particles, steam and oxygen to interact. And we take the syngas from the bottom and the slag or ash, whatever is left from the bottom. It can be used for large scale plants. In this, no tar is produced, less methane and carbon dioxide is produced in the syngas. Last one is plasma gasifier. Plasma gasifiers can be used for any type of waste. It can also be used for hazardous waste also. What happens in this gasifier is that high voltage is applied through two electrodes, and due to high voltage, electrons electrons are excited, and these electrons go and coincide with the adjacent molecules in the biomass, and again more electrons are produced, and basically a flow of electrons are produced, which generate very high temperature in the range of 4,000 to 7,000 degrees centigrades. And because of this high temperature, the biomass is decomposed into syngas components. Here we do not get any tar in the syngas. Also, the best efficiency we get from all the 4 types of gasifiers is the plasma gasifier. Also, the slag produced here is of very high quality. We can easily extract the metals and other elements from the slag. So, after extraction, very less amount of waste is present, which needs to be landfill. So the landfill requirements is very less. So it is written no landfill requirements. Next is plasma gasifiers. So here the mechanism is given is that high voltage is applied and free electrons are generated, and because of these flow electrons, more free electrons are produced and a stream of free electrons is produced. These free electrons, what happens is these go and bombard the molecules and create different types of radicals like oxide, hydroxide, nitrogen radicals. And these radicals go and participate in the chemical reaction to form the final product, which is our syngas. Here is a comparison for all the 5 types of reactor based on what is the typical particle size of the feed to be sent and what is the moisture percentage in the biomass to be used as feed. We can see here that for plasma gasifier, there is no limit for particle size or for the moisture content. We can use any type of waste for plasma gasifiers. Next, these are some of the companies which have patented the different these are some of the technologies which are used, which are there for different gasifiers. So next, it is a plasma flow chart for plasma gasifier. Here, this is gray one is the plasma gasifier. Here, waste is applied, and whatever from the slag we recycle materials, and whatever glass is there we recycle that. And the flue gas is first sent for cleanup. After cleaning, the fuel gas can be used to run the gas turbine to generate electricity, and on the steam from the flue gas can be used to run steam turbine to generate electricity. And finally, we can do distillation of the steam to get distilled water. So these are some of the biomass and waste gasification plants and we can see that majority of the end product is used for electricity production. Next is comparison between gasification and combustion. In gasification, what we do is we provide control amount of oxygen to convert our biomass into some useful or valuable gaseous product. But in combustion, what we do is we provide ample amount of oxygen or air to oxidize the biomass to CO2, H2O, SO2 or whatever the composition of biomass is there. So in gasification, we get char, that is the char or slag. Char is the fuel, or slag can be used as construction materials, or the metals can be extracted from these slag. But in combustion, the final product is a very high temperature flue gas, and other is the ash, which needs to be landfilled to prevent it from resuspending in the atmosphere. So combustion is done at atmospheric pressure, or gasification can be done at both at atmospheric or high pressure. So after the syngas is produced, we need to do certain modification for this to the syngas to further utilize for different purposes. First, we need to cool the syngas, and then conditioning is required to modify its composition. In syngas cooling and conditioning, what we do is first acid gas removal, whatever H2S or whatever sulfide in the form of H2S or COS is present, we need to remove that. Then we do shift reactions to enhance its composition. So some of the uses of the syngas are, syngas is used to make methanol, FT synthesis, DME, higher alcohol, SNG or hydrogen. So here is a syngas. It can be used for making hydrogen, electricity, SNG, FT liquids, methanols and derivatives. Next. So first we need to reduce the syngas temperature. Then we need to remove certain chemical species like H2S that can corrode or foil the system components. Next, we have to improve the purity of syngas. Basically, what we have to do is we have to remove H2S and CO concentration as well as the CO2 concentration. After removal of these gases, we have to adjust the hydrogen to carbon monoxide ratio. Because generally hydrogen to carbon monoxide ratio nearly 2 is required for various purposes. So first step is syngas cooling and conditioning. Here what we do is we do first sulfur processing, is that we remove sulfur from the syngas. Here a chart is shown where raw syngas, which contains of hydrogen, CO, CO2 and these contaminants are taken to a reactor where due to hydrolysis, COS is converted to CO2 and H2S. So whatever H2S is there, then acid gas removal is done where H2S is entrapped and whatever CO2 is either released to the atmosphere or it is sequestrated. Then whatever H2S we have entrapped, it is used for sulfur recovery. Next, the technologies which we use for syngas, use for removal of the impurities from syngas is first is absorption, in which a solvent, here you can see in the left a reactor, in which dirty syngas is provided from the bottom and some solvent is added from the top. So whatever impurities will be present in the syngas, that will get absorbed in the solvent and we can get pure syngas from the top of the reactor. So some of the solvent absorption based techniques are based on 3 methods. First is MDEA, second is Selexol and last is Rectisol. So in MDEA, chemical absorption takes place, but in Selexol and Rectisol, physical absorption takes place. Now here is a comparison between the 3 processes, MDA, Selexol and Rectisol. The comparison is based on the percentage removal of H2S and COS, and these are developed by different companies. You can go and see in the NPTEL portal about these. Next is what we do is, suppose we have H2S, how we will convert that H2S for sulfur recovery. We can do it by using any metal oxide. Here zinc oxide is used, and through reaction of zinc oxide to H2S, what we get is zinc sulfide at the temperature of 315 to 530 degrees centigrade. And again, zinc oxide is reacted with oxygen to produce SO2. So we have got SO2, sulfur dioxide we can use for sulfur recovery. We can use Claus process, or we can go for direct sulfur recovery, in which SO2 is reacted with hydrogen or CO to produce sulfur element. Or we can use this SO2 to produce sulfuric acid. So here is a Claus process shown where H2S is first reacted with oxygen to produce SO2. Then SO2 is again reacted with H2S to produce elemental sulfur. So after adding these 2 reactions, this is the final reaction, and we use one catalyst here, that is aluminium oxide or iron oxide. So I have told you to improve the composition of to improve the purity of syngas, we use shift reactions. There are 2 types of shift reaction. First is high temperature shift reaction, or second is low temperature shift reaction. We do HT shift reaction in the range of 320 to 4 degrees centigrade using this iron or chromium oxide catalyst, or we use low temperature shift reaction at the temperature of 200 to 250 degrees centigrade using copper, zinc oxide or aluminum oxide catalyst. So here are two types of speed shift or source shift. It depends upon how many cycles of high temperature shift reaction or low temperature shift reaction we are using. You can refer these from the lecture. So here, after doing the conditioning and cooling of the after swift reaction, what happens? We have the syngas whose composition is like this, that we have 43.01% hydrogen and 49.98% CO. After swift reaction, hydrogen composition has increased to 61 to 53% and CO composition has decreased to 1.12%. So here is Fischer-Tropsch synthesis. It is used to convert the syngas to diesel or wax or naphtha. What happens is carbon monoxide is reacted with hydrogen to form a CH2N monomer. And again, CO can N number of, here we can put N as 1, 2, 3, depending upon what compound we need. And CO can be reacted with 2N plus 1 H2 to produce paraffin. The general formula for paraffin is CnH2n plus 2 plus NH2O. Or we can produce olefins by using this reaction. So you can go and have a look of this flow chart. This is also, we'll move forward. Next is, first utilization is methanol synthesis. What happens is biomass is gasified. We got syngas. Next, what we'll do is we can use either to make electricity or we can make methanol out of this syngas. We're here to make methanol. We need a catalyst, which is copper oxide, zinc oxide, aluminum oxide. So there are two important processes for methanol production, and these two processes are patented by ICI or LURGI. So you can go and refer to these in the lecture, how we make methanol. Next is DME synthesis. We can make DME through two paths. First, we make methanol and then we convert methanol to DME, or we directly produce DME from syngas. So here it is a chart for DME synthesis. We have gasifier. Then from gasifier, we make methanol. From methanol, we can make DME. And from DME, it is finally separated. So these are the reactions and properties. You can refer the slides. Next is higher alcohol synthesis. We can produce higher alcohol. First, we have produced methanol, or we can also produce higher alcohol from the syngas. We have CO and H2 in the syngas. Using these reactions, we can produce higher alcohol. Of course, we require some catalysts. These are the catalysts used for higher alcohol synthesis: molybdenum sulfide with promoters, copper, cobalt, chromium, rhodium, and other groups 8 metals. You can refer these slides in the lecture. After methanol, DME, and higher alcohol, next uses of syngas is SNG production, in which we produce methane by reacting CO with hydrogen, and these are some of the catalysts which are required. Next, we will discuss about pyrolysis. We have first discussed combustion, then gasification, and next is pyrolysis. In combustion, we burn the biomass in ample amount of air or oxygen. In gasification, we provide control amount of oxygen. But in pyrolysis, we do not provide any oxygen, or if it is provided, it is very limited in amount. What happens? pyrolysis is a thermochemical reaction in which a compound is converted to simpler ones by providing heat. So first we will discuss what is pyrolysis. So pyrolysis is a thermal decomposition of carbonaceous material by heat in absence of oxygen. Suppose we have any biomass or waste, we are providing heat, and the end product which we will get in pyrolysis is char, which is the solid. We will get bio oil, which is liquid, water plus gas. In pyrolysis, we get liquid, solid, as well as gas. So here is a diagram shown. Like here is the biomass. We are providing heat and we are getting gas, char, and bio oil. So depending upon the temperature and how much time we are doing pyrolysis, the end product will depend upon that. Suppose we have a biomass and we are doing the primary decomposition at 450 to 550 degrees centigrade, but at less than 1 second. Then the end product will be gas, char, and volatile. Again, these volatiles can be converted to bio oil and gas by heating at 400 to 500 degrees centigrade for greater than 1 second. So what end products we will get from pyrolysis, it depends upon what is the temperature, what is the resident time in the reactor, what is the heating rate, and what is the feed size. So here is a diagram showing pyrolysis. The center, this one is the pyrolysis reactor. It is kept inside a furnace to provide the temperature. And in pyrolysis, by temperature, we decompose the waste. Also, we need one carrier gas to carry the volatiles and gas produced in the pyrolysis reactor outside of the reactor and is collected. So what happens in pyrolysis, we are getting all the three components. It is here condenser is provided in which the gas is condensed to get the bio oil. We get the bio char or solid from the end product, and also we get gas. So here are some of the pyrolysis technologies provided, and what is the and each technology has different temperature range, heating value, resident time, and the end product is what we will get. The end product is very much dependent upon what is the operating conditions inside the reactor. Suppose if we want charcoal, then we will use the temperature in the range of 350 to 500, and heating rate will be very low, and residence time will be hours to days. But if we need liquid and gas as the end product, then the temperature range will be high, heating rate will be high, and also the residence time will be very less as compared to carbonization. These are some of the technologies. Please refer the slides. Next, here a graph is shown between yield and temperature. We can see from here that if we, for biochar, with increase in temperature, there is decrease in the yield. And for bio oil, there is optimum bio oil production at certain temperature. Then again, there is decrease in bio oil. And for gas, with increase in temperature, there is increase in gas production. So whatever our requirement is, if we need biochar, then we will use lesser temperature. If our requirement is bio oil, then we will find out what is the optimum temperature. And if we need gas, then we will work at high temperature. And we can see from this graph that anyway water content is almost similar with the varying temperature. So here is a flow sheet. We have a pyrolyzer, then we have a separator from which we are getting the char, and after the whatever the flue gas we have got, we condense it and we get the bio oil. And we get the gas after the treatment. Gas can be used for further, gases are either further processed or it is clean and then released in the atmosphere. So please refer to slides for these. So here is application of pyrolysis product. So we are getting all three components, gas, liquid, and char from the pyrolysis. So we can use the char to either use as a fertilizer, or we can use char to produce activated carbon. We can use liquid to produce bio oil. We can also we can further modify it for other purposes, like we can use this liquid to produce heat and run turbine to produce electricity. We can also use the bio oil in transport as transport fuels and other uses. So various chemicals and fuels from pyrolysis bio oil. What are the chemicals we can get from pyrolysis bio oil? Is we can get resins, fertilizers, flavors, adhesives, acetic acid, industrial feedstocks. And the fuel which we get is hydrogen, upgraded H2O, syngas, etc. So here are some of the properties of bio oil. Why these are some of the properties, and what are the reason for these properties it is given. Please refer the slides for this. Next we'll discuss what are the advantages and disadvantages of bio oil. First, we will discuss what are the advantages. Anyway, what we are doing is we are converting waste into usable components. So obviously it is a sustainable source of energy. Next is in pyrolysis, we are getting bio oil. So it is very easy to transport oil, but it is very difficult to transport gas, which we are getting from gasifiers. So storage and transportability of liquid fuel is one of the advantages of pyrolysis. Next, whatever fuel we are getting is highly dense because we are getting in the form of liquid. Next, what are the disadvantages? So major disadvantages for pyrolysis will be that environmental safety and health issues, because there may be a chance that the workers, we will be dealing with the waste material, so there is a chance of contamination from the waste. Also the flue gas which will be released in the atmosphere, it should be cleaned, and there may be chance that there is some leakage from the gas chamber as well. Next, please refer these for these in the slides. So some of the pyrolysis reactors used are given below. These are the fixed bed, fluidized bed, circulating fluidized bed, ablative reactor, rotating cone reactor, vacuum pyrolysis, auger or screw reactor. So pyrolysis is generally a new technology, and lot of research is going on in this technology all over the world, and these are some of the reactors developed. So first is fixed bed reactor. It is simple to design and operate, and it is very reliable. Here the bio oil yield is generally 35 to 50%. So if you are using fluidized bed reactor, it is very easy it is scalable. It can be used at large scale. Generally, the particle size is the limit in fluidized bed reactor, because as we know, in fluidized bed, everything is in motion because of the high air velocity provided. So the biomass to be fed in fluidized bed reactor should be less than 2 mm in size. So here the bio yield is 70 to 75%. Next is circulating fluidized bed. It is here also after pyrolysis, whatever the biomass is present in the flue is recirculated back to the previous reactor. And here the bio yield is 70 to 75%. Next is ablative reactor. In what happens, here is a hot surface plate, and this is the biomass. What happens is pressure is provided to decompose the biomass into smaller components. Here the bio oil yield is about 70%. Next is rotating cone reactor. Here bio yield is about 65%. What happens, there is a reactor in which centrifugal force is provided. The reactor rotates, and in doing so, heat is provided and biomass is converted into so less complex compounds, and we finally get vapor, gas, and obviously there will be some gas which have to be released in the atmosphere. So here the bio oil yield is nearly 65%. Again, it is next is vacuum pyrolysis reactor. In here the bio yield is around 30 to 50%. Next is auger screw reactor. Here bio oil yield is 30 to 60%. And finally plasma reactors. Here bio oil yield is 30 to 40%. Here is a comparison given between different types of reactor. What is the yield? What will be the feed size? What is the gas requirement, etc. So please go through slides for these reactors. Here some of the examples and are given. What in suppose in Canada, what is the technology used? What is the capacity? And what is the fuel used? And these all are patented. Next we'll move. So application of char. From char we can get solid fuel. We can also make biochar and use as fertilizer or soil conditioner. We can make activated carbon from these biochar, or we can use these modify these biochars and use as an adsorbent to absorb contaminants from soil or air or water. So please go through the process to make activated carbon. So we'll start discussing. So I have given a brief recap about what is the technology, what are the reactors used. I request you all to just go through the lectures in the NPTEL portal and you will get everything. So till now, if anyone have any doubt, then you can ask me.
Yes, madam. Actually, for gasification, we are selecting raw material from the waste. We are selecting the waste as a raw material, right, madam?
Yes.
Fine, ma'am. Which are the characteristics? So we need to look into that selected raw material. Usually, I think
Sorry.
carbon, hydrogen, connect, right, madam?
End product. Huh? So can you
No,
please repeat your question? I just
no,
didn't
the
get it.
selection of raw material for the gasification process. Which properties we have to look from the feed?
Okay, so you're asking which property to look in the feed for gasifying it.
Yes, ma'am.
Okay. So the municipal solid waste is any solid waste is collected by the municipality. It is taken to the facilities for separate segregation, recycling, and all. And see, what happens is majority of the waste is incinerated all over the world. But the end product we get from incineration is very high temperature fuel gas, which we use for energy production. But slowly gasification and pyrolysis are developed, and these technologies are developing because the end product which we get from pyrolysis and gasification can be used for industries as a raw material, or we can use it for electricity production as well as for other like we can get hydrogen, alcohol, and all. So these technologies are very much developing, like pyrolysis and gasification. Hello.
Yes, yes, madam.
So these are new technologies which are being developed as compared to incineration.
Okay, ma'am. But if I have a waste, municipal waste, so I want to do gasification or incineration. I have had idea. I had idea that processing, but is that that waste is suitable for that? We can't go directly in plant side. Otherwise, we have to do pilot scale study, right, madam?
Yes.
before going to that, how much we will get the yield also. We have to
Yes,
do
yes.
pilot scale study. Otherwise,
Yes.
carbon from the RM content or heating value, anything we have to check before proceeding to the plant scale.
Yes, yes. First, we have to do the pilot scale study, then we can establish a lab scale plant. See, you are talking about properties. We need to check the moisture content first,
Yes.
because we have seen that incineration we need dry waste, but in gasification or in pyrolysis, we have seen that there are very efficient reactors like plasma gasifiers, in which there is no boundation for moisture content or the particle size also. So, but what happens is the plasma gasifier is costly than other gasifiers. So it will depend upon what we need as the end product, what capital cost we can invest, what is the technology available.
Okay. So the pretreatment required for incineration, right, ma'am? It is it won't burn
Yeah.
if it won't burn if it is wet. And for
Yes.
gasification also, we are for gasification and yes, for gasification we are feeding steam. We are along with the steam only it is going. Our feed is for heating purpose.
Yes. We are using
Okay.
both steam and air for gasification.
Yes, ma'am. But for pyrolysis, we are hitting that raw material indirectly, not directly.
No, we are providing heat externally in the pyrolysis reactor.
Yes, madam. Externally, but it's not contact directly with the raw material, means waste.
No. Okay. You have any other doubt?
No, madam.
So we'll discuss the questions. Previous year assignment 3 questions. There is no numerical in this question. At the end, we will solve one numerical. So first question is, the Selexol process uses Selexol solvent, a physical solvent which is made of methyl diethanolamine, DPG, methanol, or citric acid. You just write your answers in the chat box, or you can also unmute yourself and you can see the answer. So I'll give you 1 minute for this question. Please write your answers in the chat box. I've got only one answer. So the answer is B, dimethyl ether of polyethylene glycol. So we can refer this slide. It is sorry, direct question. Where it is written that for solvent absorption, we use in Selexol, we use dimethyl ethers of polyethylene glycol. The next question. Next question is catalyst used in Claus process for recovering elemental sulfur from gaseous H2S is. Just write your answer. It is also a direct question from slide. I'll give you 1 minute for this. Just try to answer in the chat box. So the correct answer is C. It is also a direct question from the slide. Like here it is given for Claus process. We need aluminium oxide or iron oxide to convert SO2 to elemental sulfur. We'll move forward. So it is also a direct question from the slides. What is the general formula of paraffinic hydrocarbon? You have 2 minutes, 1 minute. Just try to answer in the chat box. I got only one answer. Please just try to answer. So I need participation from you guys. Just please try to answer in the chat box. So correct answer is A, CnH2n plus 2. It is also a direct question from the slide. Here it is given for paraffin. The general chemical formula is CnH2n plus 2. So we'll move to next question. The conventional methanol synthesis technology uses a series of catalytic adiabatic reactor beds. Most suitable operating temperature and pressure for this process is. It is also a direct question from slide. Just try to answer in the chat box. I'll give you 1 minute for this question. I need more answers. I just got one answer. Please try to answer in the chat box. 2. Okay. Answer is B. The temperature range is 220 to 250 degrees centigrade and the pressure is between 5 to 8 megapascal. Next is identify the process for the schematic diagram given below. This is the diagram. We have to identify which process this shows. First is genoyl hydroconversion upgrader, Mirox process, solvent extraction, dimethyl ether synthesis. So I'll give you guys 1 minute. Just write your answer in the chat box. I need more answers. Please write your answer in the chat box. So correct answer is D. This figure shows DEM synthesis. Next question is again we have to identify the diagram. Here it is. Identify the process from the schematic diagram given below. Entrained bed gasifier, plasma gasifier, fixed bed gasifier, or fluidized bed gasifier. So you have 1 minute. Just try to answer in the chat box. I need participation from everyone. I'm sorry, I was mute. So the correct answer is plasma gasification. It is also a direct question from the slide. We just have to identify the gasification reactor by seeing the picture. Next question is bio oil yield for auger or screw reactor is. It is also a direct question. Just write your answer in the chat box and I need participation from everyone. I'm only getting 1 or 2 answers. Please everyone write your answer in the chat box. At least try to solve. If you're not getting the correct answer, no problem. Just write your answer in the chat box. So I'll give you 1 minute to solve this question. And I need answer from everyone. I need 2 more answers. So correct answer is C, 30 to 60%. It is also a question from the slide. You can see for auger or screw reactor, the bio oil yield is 30 to 60%. So basically the assignment 3 questions are based on theory of whatever is what is taught for incineration, sorry, for gasification and pyrolysis. Next question is which of the following method of methanol synthesis employs a homogeneous nickel catalyst and alkoxide in an organic solvent? It is also a direct question from the slides. Just write your answer in the chat box. I'll give you guys 1 minute for this. I just got 3 answers. I request everyone to write your answer in the chat box. There are 5 participants and I got 3 answers. I need 2 more answers. Okay, so the correct answer is B. Nickel catalyst and alkoxide is used in Brookhaven National Laboratory method. So it is also a direct question from the slide. Like for Brookhaven National Laboratory method, nickel catalyst and alkoxide is used. So we'll move to next question. So the question is find out the correct statement given below. We have to find out which of these statements are correct. Basically, one statement is correct. So I'm giving you 1 minute. I need answer from everyone. So first I'll get 5 answers, then only we will proceed to next question. Guys, write your answers. I got 2 answers. I got 3 answers. I need 3 more. Everyone write your answer. Okay. The correct answer is B, that DME has very high cetane number. Next question. This is the last question of the assignment. So here you can see the properties of DME is that it has low auto ignition temperature, very high cetane number, high oxygen content, and very low particulate emissions. So the correct answer is B, that DME has very high cetane number. Next question. Syngas feed is characterized by R value, that is hydrogen content minus CO content upon CO plus CO2 content. The desirable R value for methanol synthesis is, it is also a direct question and it is used number of times during the lecture. So I want answer from everyone. Just write the option or whatever answer you think, 2, 4, 3 or 1 in the chat box. We'll wait for 2 minutes. So I got 3 answers. 3 people are left. Please write your answer in the chat box. I'll wait for 1 more minute. Okay. At least I need 1 more answer. I need 1 more participation and then we can move to next. Okay, we'll move forward. I have got only 3 answers. So the correct answer is C, 2. The R value for methanol synthesis should be around 2. So since the numericals for pyrolysis and gasification are discussed in the next week 4 materials, so we will try to solve the questions based on pyrolysis and gasification in the next discussion hour. Today what we will do is in the last live session we have solved 2 or 3 numericals based on incineration. So today what we will do is we will solve one numerical. It has 3 or 4 parts. It is also based on incineration. I will give you all the initial data, concept, formula required. I will first explain you how to solve it, and then you will solve. So the question is, estimate the overall moisture content of a sample of as collected residential municipal solid waste with the typical composition given below. So here is the composition. The questions which we have solved in the last week, direct composition in terms of direct elemental composition was given. Like we were given how much carbon, hydrogen, oxygen, sulfur content is there in the MSW. But here we are given a typical MSW composition. Like what are the components basically present in the MSW? These are the components, their weight percentages are given and their moisture content are given. So first of all, my question is, after seeing the composition of this waste, can anyone tell me what the composition of waste signifies, whether it is from a low income country or a middle income country or a high income country? You all got my question?
Sorry, ma'am, can you repeat again?
So I'm saying that suppose you are given this waste for MSW composition waste. This is the composition of the MSW waste. You have given the different components and different weight percentages. That out of 100%, you have organic food as 9%, paper as 34%. So after looking at this composition, what we can say or what we can conclude about from which country we can expect this type of waste, either from a low income country or a middle income country or a developed country. Now my question is clear.
Yes, madam. Organic food, paper, cardboard. So the low income country.
Okay. I want answers. You are telling it is a low income country. So can you tell me what is the reason?
The organic food.
So what? Organic food?
Sorry. The containers, tin, yard waste, wood. Sorry. The developed country. I didn't see in the
Developed
bottom
country.
side. Yes.
Okay, I got one answer from Shubhangi from developed country. So I want the reason why you think it is from some developed country. Shubhangi, you can unmute yourself or you can write the reason in the chat if you're not comfortable. Also, Venkatation, you can unmute yourself or say, or you can write your answer in the chat box. Anyone? What is the answer?
Right, ma'am. I got a strong answer that low income country because we are the waste is paper only. There is no electronic waste also, and majority is paper waste only, and the miscellaneous tin only. So minor there is a usage of less usage of tin and inorganic glasses and all. So the low income country.
Okay. So Shubhangi is telling it is from a developed country because packing material is used for packaging. So the answer is it is from a developed country. So I got one more answer from Adarsh, that the overall energy production from a waste to energy plant depend upon select the most. Sorry, Adarsh, you have just written a question. Can you just unmute yourself? So you have posted a question here. Do I need to answer this question? Okay, it is a assignment question. So it is from which week? Can you just tell me? Adarsh, can you tell me it is from which week?
Ma'am, it is on the assignment number 4, and the question, and actually the question is all about uh, the question is all about the overall energy production from waste to energy is depend upon which kind of waste, like heating well waste, thermal efficiency, or efficiency of turbine units.
This is for week 4, but we are discussing for week 3. So is the deadline over? Because after the deadline is over, you will get the solution.
Okay, ma'am, no problem.
Okay, I can't tell you the solution before the submission date is over.
Okay, ma'am, okay, ma'am. I can totally understand.
So we'll come back to this question that it is composition is from a developed country. What reason vegetation is giving is just opposite. Whatever reasons is giving, it is for the developed country. See what happens with increase in prosperity, there is increase in municipal solid waste generation. Suppose you have a low income country. If the income is low, then majority of the income is spent on food and other basic needs. So the content of food waste will be very high in low income sectors. Then with increase in income, prosperity, there is an increase in other waste materials, like there will be increase in paper, cardboard, metals, etc. So here we can see that the organic food content is only 9%. But we can see that paper constitutes 34% of the total waste. And there is also a very high amount of cardboard, plastic, textiles, yard waste. We have considerable amount of metals, aluminium. So it is from a high income country, not from a low income country. So we'll move forward. We have given the overall moisture content. For organic food, it is 70%. For paper, it is 60%, and so on. And we have given the weight composition. After adding all these percentages, we will get 100%. So we have to find out what is the overall moisture content of this MSW. So first we will take a basis. We will take the basis sample as 100 gram, and we will do all the calculation based on this 100 gram of MSW. So I'll give you the formula. 1 second. So for moisture content is equals to wet weight minus dry weight into 100 upon wet weight. So we have given what is the moisture content, and we have given the MSW, what is the total MSW provided. Suppose we are given 100 gram of MSW, out of that 100 grams, we have 9% organic food. So we will calculate how much organic food we have, and then we will find out dry weights of these organic food and wet waste, and then we will find out what is the moisture content. So you got the question, everyone? Like anyone have any doubt?
Yes.
Everyone
No,
got
ma'am.
the question?
Yes.
So basically we have to find out what is the moisture content of this MSW provided. We have given the individual moisture content, and we have been provided the what is the weight percentages of each component. So what we will do is, for suppose organic food, we have given that 9% of the MSW is organic food. We will take basis as 100 gram. Out of this 100 gram, 9% is organic food. So the wet waste of organic food will be 9 into 100 upon 100, that is 9 grams. And out of this 9 gram, 70% is water. So 30% will be the dry matter. So we will find the dry weight as 30 into 9, that is 2.7 grams. Now everyone got it? So similarly, for each component, we will find out what is the wet waste and what is the dry waste. We will sum of the wet waste for each component, and we similarly will find the summation of dry weight for each component. And after that, we will put the total wet weight in and total dry weight in this formula, and we can find out what is the overall moisture content. Now am I clear? Anyone? Like if you're having doubt, you can just unmute yourself and ask. So I think no one is replying. I think it is clear. So
Yes, ma'am. Yes, we are doing that. I'm doing.
I'll give you, big since it is a very, you have to do lots of calculation. So I will give you 5 minutes to find out the moisture content of this MSW. So I request everyone to just solve this question. No problem if you're getting the wrong answer because it is very lengthy and calculation. So just find out the answer and write your answer in the chat box. I just want everyone of you to at least try to solve this question. So I'll give you 5 minutes to start solving. See, what we'll do, since it is a very lengthy question, we will find, you just solve for organic food, paper, cardboard, and plastic. What is the dry weight and what is the wet weight of these four? And then we will proceed towards moisture content. So I'll give you 4 minutes to find out what is the wet weight and dry weight organic food, paper, cardboard, and plastic. I got only one answer from Shubhangi. So try to solve for other components. I will give you 3 more minutes to solve for these other components. It is a very simple calculation. For 100 grams wet weight will be equal to the weight percentages, and out of that you just have to subtract the moisture content. So I got 2 answers, and Rachna is asking is that some value is not given in assignment 5. So Rachna, you can ask this question on the portal. There is one section for posting the questions. You post your question there, and from NPTEL team, you will get the reply through mail. So Rachna, am I clear?
Okay, ma'am. Thank you.
So I got 2 answers. Please, I need more answers. It is a very simple question. No, in any mail ID where you see the NPTEL lecture, there is one section to ask the question also. You can post your question there. So I'll discuss the answer. So we have been, it is better to make a table like this. For each component, we have given the weight percentages and moisture content. So for paper, 34% waste is paper, and we have 100 gram of waste. So wet weight will be 34, and out of that, 6% is moisture content. So 96% is dry matter. So we will multiply 0.96 into 34, we will get 32. Similarly, for inorganic glass, weight percentage is 8. And moisture content in glass is 2%. So 98% is dry inorganic glass. So 0.98 into 8 will give 7.8 gram of dry weight of inorganic glass. So we'll calculate for each component what is the dry weight, and wet weight will be equal to the weight percentages because we have taken 100 grams and weight percentages is for after adding these we are getting 100%. So if 9% is organic waste, so organic food waste, so wet weight of organic food is 9 grams. So after calculating the dry weight and adding it all for all the components, we are getting the dry weight as 78.8 gram and we have wet weight as 100 grams. So we will put in the formula. So moisture content will be 21.2%. So I got two answers and both are correct, 21%. So we'll move to next question. So anyone have any doubt in this question? So no doubt. So we'll move to next part of the question. So here we have to find the chemical composition of the waste. Typically we have to find the what is the chemical formula for this waste. So we are given the elemental composition of each waste. We have organic food waste. We have given how much percentage is carbon, hydrogen, oxygen, nitrogen, and sulfur. And these percentages are given on dry basis. Like out of the whatever, like for organic food waste, we have dry weight as 2.7 grams. So out of that 2.7 grams, we have 48% of carbon, 6.4% of hydrogen, 37.6% of oxygen, 2.6% of nitrogen, 0.4% of sulfur, and 5% of ash. So for each organic fraction, we are given the elemental composition. We are also given elemental composition for inorganic waste, but we have to find the chemical composition of the organic fraction. So what we will do is we will find for each organic component of the waste what is its carbon, hydrogen, oxygen, nitrogen, and sulfur content. So am I clear? Can anyone confirm whether you got?
Yes, madam. Okay.
Okay, so first we will calculate the elemental weight of each of these organic components, then we will proceed with the question. So I'll give you 5 minutes. So just try to solve it. I didn't get any answer. I can understand it is very lengthy question. We have to find individually for each component. So I'll move towards the solution. So first, what we'll do, we'll set a table so that we can do all the calculation in the table. So here we will make a column for component. We need to find the molecular formula for the organic fractions. So we will write all the organic components. We know what is the weight composition. So we will first find the wet weight, and we have already found the dry weight and wet weight in the previous question. So we will copy from here, and now we are given what is the carbon percentage in food waste. Carbon is 48% on dry basis. So we will find out what is the carbon element, like 48% out of dry weight, that is 0.48 into 2.7. We will find the carbon content as 1.3. Hydrogen is 6.4%. So we will find out hydrogen as 2.7 into 0.064. We will find the hydrogen as 0.017. Similarly, we will find the oxygen, nitrogen, sulfur, and ash content. So we will do this calculation for each organic element, organic component, that is organic food, paper, cardboard, plastic, textile, rubber, leather, yard waste, and food. And after this, we will add what is the carbon content in overall waste, what is the hydrogen content, what is the oxygen content, nitrogen, sulfur, and ash. So we got a wet weight as 79.5%. Sorry, 79.5 gram of out of the 100 grams is organic components. And out of this 79.5 grams, 58.4 grams is dry weight and the rest is moisture. And on the basis of dry weight, we have 27.39 grams of carbon, 3.62 gram of hydrogen, 22.97 grams of oxygen, 0.4 grams of nitrogen, and 0.10 grams of sulfur. So suppose we have got all the elements mass, that what will be the mass of carbon, hydrogen, oxygen, and others in the MSW waste. So next what we have to do is we have to find the chemical composition, that is the chemical formula with and without sulfur and with and without water. So we will get 4 chemical formula: one with water, one without water, one with sulfur, and one without sulfur. So suppose you have got these values, like carbon is this much grams, hydrogen, oxygen, nitrogen, sulfur, ash. Now try to find out what will be the formula. So I will give you a hint, like you have 27.39 grams of carbon. You know what is the molecular weight, atomic weight of carbon. So we'll calculate the number of moles of carbon. Similarly, we'll calculate number of moles of hydrogen, oxygen, nitrogen, sulfur. So for without water, it is a very simple, straightforward question. You just have to find out the number of moles of each element, and then we can simply get the chemical formula for the MSW. So first try to find out what will be the chemical formula without water. So I'll give you 3 minutes. Just try to solve because we are running out of time. I have one more question to discuss. So everyone, please try. Anyone have any doubt till now that how to proceed with this question? So we'll wait. I'll give you 3 minutes to find what is the molecular formula without water and without sulfur. After finding the formula, just write your answer in the chat box or just unmute yourself and tell what formula you got. So I got two answers. So we first find out what is the moisture content. Dry weight is 58.4 and wet weight is 79.5. So we'll find out.
Are you looking for celebrity?
Sorry. Moisture content is 79.5 minus 58.1, that is 21.4 grams. Okay. So next is, we'll prepare a table like this. For carbon, we know first we'll do the calculation for without water. For carbon, it is given as total carbon content in organic waste is 27.39 grams, hydrogen is 3.62, oxygen is 22.97, nitrogen is 5.54, and sulfur is 0.18. And ash is given as 3.48, but the molecular mass of ash is not given, so we will not do any calculation for ash. So we'll find out what is the number of moles for carbon, hydrogen, oxygen, nitrogen, and sulfur. So we are getting as 2.28 moles of carbon, 3.584 moles of hydrogen, 1.43 moles of oxygen. So both the answers are correct. I got two answers, one from Shubhangi and one from Venkatesan. So both the answers are correct. Good. So we know for without water. Now we will do the calculation for with water. We know that we have 21.4 gram of water. And we know that the molecular mass of water H2O is 18. And out of that 18 grams, we have 2 hydrogen atoms. So we have 2 grams of hydrogen. So we will find out how many grams of hydrogen are in 21.4 grams of water. So we will find by solving 2 by 18 into 21.4. This much is the amount of hydrogen in moisture plus 3.62 grams of hydrogen is present in the dry weight of the waste. Similarly, we will find the oxygen content as 16 by 18 because for each mole of H2O, we have 1 mole of oxygen. So it will be 16 by 18 into total amount of water or moisture in the waste is 21.4 grams. So we will get 41.99 grams of oxygen. So after getting these, we will find out the number of moles. So again, the number of mole of carbon will be same. Hydrogen will change because it is now 6. So we will find it is 5.94. I have approximated it. And again, oxygen will be this much, nitrogen and sulfur. Now next part is we have to find the formula. We have to find out what is the formula without and with sulfur. Like we do not have to consider the sulfur in the MSW, and second we have to consider the sulfur, and for the third formula we do not need to consider water, and for fourth we need to consider water also. So what I have done is that we have nitrogen as 0.54 without water. Sorry, 0.038 moles of nitrogen without water. So what I have done, I have taken the nitrogen as 1 and divided all the moles of carbon, hydrogen, nitrogen, sulfur as by number of moles of nitrogen, that is 0.038. So we will get carbon as 60, hydrogen as 94.3, oxygen as 37.8, nitrogen as 1 mole, and sulfur we are not touching because we have to find the formula without sulfur. So these are the formula that without water we have this as the mole composition. With water we have this mole composition, and for sulfur, like we are considering here sulfur, so we will divide all these values by number of moles of sulfur. Here we have 0.003 moles of sulfur for without water and for with water. So we will divide all the number of moles by 0.03 and we will get these number of moles without water and these number of moles of different elements with water. So our end formula is these. Like without water it is C60H 94.3 O37.8 and N. What you guys have done is also correct, but the number of moles are more in decimal, so it looks complicated. So you can simplify by taking the element which has least number of moles. You can divide all the elements by that number of moles and you can get a simplified formula. So we'll move forward. So anyone have any doubt? You can ask me if you didn't get anything or you have any doubt in this question.
Madam, actually the syngas can be burned again. Can we, it will combust again, madam. That having hydrogen and TO. So is that it will combust again? Means
Yes,
after
yes.
production syngas.
After syngas, it is used for various purposes. Like we can combust CO and convert it into CO2. and we can get energy which we can use to run the turbines. Obviously, syngas is can be combusted.
Fine, ma'am. And the syngas production is the exothermic, right, madam?
Combustion, if you are converting CO
No,
to
no,
CO2,
syngas. Yes, madam. Syngas production, I must.
we are providing heat and we will get the we are getting the syngas which temperature is around 200 to 350. So it
Okay,
is.
so we yes, the syngas outlet is we can use while we can use for the preheating the feed also.
Yes, it can
The
be used.
outlet syngas from the reactor. We can. Oh, fine.
Okay, we'll move to next part of the question. So here we have to find the energy content of the MSW. Here we have to determine the energy value of typical residential MSW with the average composition determined, including sulfur and water. So the chemical composition of the waste, including sulfur and water, is given. So sorry, just ignore these lines I have given here also. The chemical composition of the waste which we have to find the energy content is this. So we can find the high heating value by using this formula in which carbon, hydrogen, oxygen, nitrogen, and sulfur are taken in percentage basis. Like suppose we have this formula, we have to find out how much percentage of carbon is in 1 mole of this, and how much percentage of hydrogen and how much percentage of oxygen, nitrogen, and sulfur is present in the MSW formula which we are being given. So I request you to solve this question. So I'll give you 3 minutes to solve this question. Just solve and write your answer in the chat box. So I'll move to the solution. So we have the formula as C760, hydrogen 91980, oxygen 875, nitrogen 13, and sulfur as 1. So we know that in 1 mole of this, we have 760 moles of carbon. So 760 into atomic weight of carbon will give us total weight of the carbon present in 1 mole of this MSW waste. So we will find out elemental weight of each, we will find out weight of each element present in 1 mole of this gas, 1 mole of this MSW, and then we will add it. So the total weight is 25314. And then we will find out what is the composition of carbon out of this total 25314. That will be 9120 upon 25314 into 100. That will be 36.03. Similarly, we will find the percentage of hydrogen by dividing the weight of hydrogen 1980 divided by total molecular weight of this, that is 25314, and we will get percentage of hydrogen as 7.82. After getting the percentage of hydrogen, carbon, oxygen, nitrogen, and sulfur, we will put these percentages in this formula, that is 0.3561 into C, this hydrogen, oxygen, nitrogen, and sulfur, and we will get what is the high heating value in megajoule per kg. So after we don't have to do anything, we just have to put the percentages here, and we will get the answer as 15.683 megajoule per kg. So am I clear? Anyone have any doubt in this question?
No, madam.
Okay, and one more thing, Venkatesan, you were asking whether gasification is a endothermic or exothermic process.
Yes, madam. Yes.
Okay, sorry, gasification is an endothermic process because first we have to provide very high temperature inside the gasifiers.
Okay,
So
okay,
heat is provided for heating the reactors, and also steam and oxygen is applied. So gasification is an endothermic process. Pyrolysis is also endothermic, but incineration is an exothermic process.
Yes, madam.
Okay, thank you so much for joining. And this is the last slide of today's session. Hopefully, we will meet on next Sunday. If you have any doubt in between, you can just post your doubts on the NPTEL portal, or I request you everyone to join on Saturday and Sunday on time, and we will be discussing some questions. And next week, most probably, we will be discussing questions on gasification and pyrolysis, because the tutorial part of these two is in week 4. So we will do some questions on gasification and pyrolysis, and also we will try to solve the previous year assignment questions. So thank you so much for joining. Have a good night. Thank you.
Thank you.